Let's move on to problem 2. In problem 2, we are going to do a more complete, like a real lab, except the data is provided to you. So we are going to use the skills we learned in problem 1 to analyze this problem and finally get our desired quantity and write calculations, uncertainty analysis, and conclusions. Let's look at our previous example using the period of oscillations with different hanging masses to measure the spring constant. Suppose this is our raw data. You have different hanging masses from 500 grams to 1500 grams. The number of counter masses are different, which will affect the uncertainty on the mass, and we measure the period and its uncertainty. Let's see how we are going to analyze this data. So at the beginning of your calculations, you do exactly the same as you did in problem 1. You decide which quantities to plot on the axis and how you plan to calculate the desired quantity and its uncertainty. Then you need to create the graphing data table. It's a list of the X quantities and its uncertainty and the Y quantities and its uncertainty. So X is the square root of M. That's how you calculate its uncertainty. And the Y is the same as data, the period. So to calculate X, you convert 500 grams into kilogram and take the square root. You will get 0.70711. And you can plug in the numbers to calculate delta X. I will write down the number here, but I will show you details for the next row. So I will first write down the numbers here. The Y and delta Y are the same as your data. So the next row is the 700. So I'm going to show you how to do the calculate delta X. In fact, we mentioned that there are different forms you can calculate delta X. This one is the unsimplified form, but it's in fact easier to use when your graphing data has a different unit than your raw data. So I'm going to leave it without simplifying it, and I will put in the numbers. Now I can put in delta M in grams and the M in grams. Since gram will cancel, they won't affect the final unit, but I will put in the delta square root of M in kilograms. So now you calculate this out, you will get a very small number in the right unit. And then we can put it into the table, and the Y values are just copied from your raw data table. So keep on doing this until you finish the data table. And now once you have the graphing data table, you can do the graph. And you'll find on your graph paper best slope, worst slope, and the uncertainty of slope. Once you're there, you come back to your report, to the worksheet, to calculate the gravitational acceleration g based on what you planned earlier, how to find the desired quantity from the slope. So find out g here, and in the uncertainty analysis, find out delta g over g or delta g, depending on what equation you get here. What the equation you get earlier, just use that equation to find out the uncertainty of g. And conclusions, state the conclusion. The gravitational acceleration measured by dropping the water balloon is found to be this value plus minus its uncertainty, and the unit pay attention to how many digits you should keep. Uncertainty always 1 or 2 non-zero digits, and your value should match the same decimal place. There's to complete this report, compare the number to the reference value, which is 9.81 meter per second squared. There's no other discussions because we didn't do this experiment, so we cannot discuss what factors we ignore. Just do a comparison and state whether the result agrees with the reference value or not.